Recording. Well, it's a real pleasure to have Mukund give us a talk now about open quantum systems. Once again, I'll record up to the end of the talk. Feel free to ask questions during the talk. Of course, those will be recorded. And then I'll turn off the mic at the end so that people can feel free to ask wilder and woollier questions they don't want released out into the cosmos. So without further ado, Mukund, why don't you take it away?
Right. Thanks, Albion. So I'll talk about some work I've been doing over the last year and a half. And Albion actually asked me to review some of this for us. So the idea is to try to use holography, and I'll try to explain why I think it's a useful avenue to understand open quantum systems. I wrote these slides a few days ago for another conference. I'm repurposing the slides, but since they're handwritten, I'll be happy to fill in details as we go along. So feel free to interrupt me. So just to give you an outline of where this is all recorded in print. This is written in much of this is done in a series of papers with primarily with my collaborator Rangamani and various of the students and postdocs. But I also want to highlight two of our Davis postdocs, Temple Hay and Julio Virueta. The three of these papers, one establishing the framework for using holography to do open quantum systems, and the other to study open quantum systems with some kind of long-term memory arising from diffusive dynamics are out. There is a couple more papers in the works trying to understand how to think about energy transport in strongly correlated systems, which has to do with the propagation of phonons. It turns out I was hoping it would be out by today, but well, they are a bit more complicated than I wanted. Okay, so I'm going to start I'm assuming some of you already know some of this, but I'm going to start from a very basic level. So feel free to interrupt me or tell me to speed up. So I'm going to just start by talking about the general paradigm of open quantum systems and what is it that we want to do, and what is it that I want to do, which is to sort of transcend some of the discussions that you'd find typically in textbooks. So imagine a setup of the following kind. We have a probe system. I have an environment, which I'm going to have some degrees of freedom, which I'm going to call X. This is going to be my primary quantum system, but I'm going to view this slightly differently. I'm going to view this as kind of providing an environment. I'm going to stick in some probes parameterized by some degrees of freedom psi, which are going to be coupled to this environment. And I'm going to try to understand what the effective dynamics of the probe is after integrating out the environment. So in other words, I'm interested in some quantum system. So let's say this environment is some thermal plasma. And what I'm after is asking, if I stick in a thermometer or some probe in the thermal plasma, what kind of effective field theory should I write for this thermometer? Okay. And I'll give you various examples as we go along to illustrate this. So of course, we know even from the get-go that the joint probe plus environment systems evolves unitarily. So I could imagine preparing this environment probe composite where the initial state is a tensor product. So I have the initial state of the system. Rho initial is just some rho environment which I've prepared times rho probe. But as the system evolves, the joint system evolves unitarily. And so if I now trace out or forget about the environment and ask what is the intrinsic probe dynamics or the dynamics of the reduced density operator on the probe, that's not going to evolve unitarily. It's going to evolve primarily as a quantum channel. There'll be some map from the initial probe density operator to the final probe density operator. We could write various prototype examples of this with Lindbladian dynamics, but I'm going to be agnostic about what is happening. Instead, I'm going to try to figure out from first principles, if I can, what the effective field theory governing this density operator evolution is. Okay, and so in simple words, we really care about what the effective field theory of such quantum channels is. Okay, and the story is not new. The story is ancient. It goes back to the 60s, and here is a very famous paper of Feynman and Vernon, which basically laid out the groundwork for thinking about these kind of prototype problems. So if you think of the quantum amplitude given by the path integral is obtained by doing path integrating over the probe degrees of freedom, the environment degrees of freedom, and the joint action, which may start out as having factorized forms for the system, for the environment and the probe, and some interaction that comes from coupling the probe to the environment. Integrating out the environment will give us an effective dynamics for the probe, except that, as I said, we actually want to think of this as a quantum channel. We want to think of this as a positive map from density operators to density operators. So you want to actually break out what's happening not to amplitudes, but to probabilities. So that's easily done. You take this quantum amplitude, square it, and then integrate out the environment. And what you get is a structure the following form. You get two copies, if you will, of the probe degrees of freedom. I'll let them left and right, but you can think of them as the pieces that correspond to the bras and kets of the probe system, respectively, because they're coming from the density of, they keep track of the pieces of a density operator, not just a state vector. And then, because you have both these pieces, you have the forward evolution of kets coming with the intrinsic dynamics associated with the probe, the backward evolution of the bras. But then the piece that's important and the piece that governs all the interesting stuff here is this influence functional, which the phrase these folks coined, which tells you how the kets and the bras are linked to each other and how, therefore, the system evolves non-unitarily in this Lindbladian sense, in this quantum channel sense. So what we're really after, if you're thinking about this problem from a high energy effective field theory perspective, is we're asking the question, what are the constraints on these influence functionals, which are governed primarily by microscopic unitarity? There was a joint system up here, which evolved unitarily. And if you ask me to write down an effective field theory for the joint system, we know how to do this. This was taught to us by Wilson well nigh 50 years ago. So the question is, how does that translate into effective field theories for such influence function? So let me continue, before I sort of lay out the rules, let me continue in terms of examples. So Feynman and Vernon laid out a very simple prototype example that was well studied later by Caldera and Leggett, famously in their paper on quantum Brownian motion. And the prototype example is just a linear dissipative system. So we could think of my environment as a collection of harmonic oscillators in, let's say, thermal state, and my probe as a single additional oscillator that's probing this environment. So I wrote down, and there's just a linear coupling between the probe and environment. So I wrote down an environment in terms of some collection of oscillators in the state that's prepared as a thermal density operator. And the probe is just a single, in fact, in this case, a free particle. And the coupling is, I might want to put in some oscillator coupling, quadratic potential here just to do some IR regulating. But otherwise, I could just couple this linearly and see what happens. And as I said, I'm going to take the initial state to be just the thermal state on the environment, tensor the product state, the vacuum state of this probe system. And I want to know, how does this evolve? And what happens if I then integrate out the environment? So these folks, of course, solved it. And what they showed was that you could give a nice, simple, effective field theory for the probe dynamics, in this case, 1 degree of freedom. And that effective probe dynamics, we can understand very intuitively. So I have a single oscillator or free particle sitting in a thermal bath of oscillators. It's coupled linearly. So it's getting buffeted around by these oscillators that make up my environment. So first, it's going to have a linear drag. It's going to have, that's the essential feature of friction coming from the non-unitary dynamics. So that's the linear drag term, the friction or the dissipative term, with the fact that the energies get lost to the environment. But that's not it, as it goes back almost a century to Einstein and Somolchowski. There's also a stochastic noise piece coming from the fact that there are thermal fluctuations of the environment. So both of these need to be recorded, and they get recorded in the dynamics of this probe as basically quantum Brownian motion, where the probe dynamics is no longer just a free motion, it's free motion with friction and stochastic noise. But importantly, and this is the key point, that this friction and dissipation and stochastic noise, they're not independent objects. They come from the same microscopic physics. They come from the fact that the medium was thermal. And this leads to the famous Einstein-Somolchowski or fluctuation dissipation relation or Cobo-Martin Schwinger formula, depending on what your context is. And it basically says that the noise kernel is related to friction up to a factor of temperature. Okay. And so that's the level of, that's the dynamics at the level of on-shell physics or the level of equations of motion. But you can take this on-shell physics and upgrade it to an effective action. Okay. And this problem is actually very easy to do. And in fact, it predates even Caldera-Leggett's discussion. It goes back to the 70s in works by Martin C. Jarros and Dominic Spelletti and Janssen, who basically said that, you can write down, you can take the stochastic equation of motion, implement it by a Lagrange multiplier field, integrate out the noise if you assume it to be Gaussian, which is this in this case, because my noise is made up of thermal fluctuations of oscillators, and then integrate in, therefore, a quantum degree of freedom. And that quantum degree of freedom coupled with this classical degree of freedom, which is this classical oscillator piece, gives you what I would call the effective Schwinger-Keldysh action, which has the following structure. So there is, and the structure is going to be important, so let me spell it out. So I had here two sets of degrees of freedom, which I referred to as the right and left, or the Kate and Brad degrees of freedom. I'm going to make a basis change and take the average and difference and refer to them as a classical and quantum degrees of freedom, respectively, as is conventional in various discussions. From the point of view of integrating in the quantum degree of freedom into this stochastic classical equation, the quantum degree of freedom is the difference field. The classical degree of freedom is the average field. And the structure is that the average field couples the difference, and the difference has self-coupling, which gives you both friction, it gives you the noise. So think of QD squared as coming from integrating out a noise kernel, which was F squared ON. Is that a question? Okay. So that's the prototype problem that one has. And this problem is pretty easy because everything here is Gaussian. Noise is Gaussian, and the whole problem you could have just started with the path integral for this coupled oscillators, carried out the integrals because you're just doing Gaussian integrals. But not all noise is Gaussian. So how do we deal with this in general? And in quantum mechanics, it's not so hard. You can imagine generalizing what I just said to including non-Gaussian noise. In fact, you can go a lot further than that. So I have been focusing here on retarded response friction that comes out of trying to disturb my medium by turning on a source and watching how that slows down the propagation of my probe particle. But you could ask more interesting questions having to do with correlation functions of Heisenberg operators of the probe or of your system, which are not particularly time ordered. They're of various kinds of time, various out of time orders. And one can actually indeed go ahead and in quantum mechanics derive an effective field theory for such probe dynamics. This was done in a paper a few years ago by Chaudhary and Loganayagam, which I highly recommend because they actually worked out for the first time in my knowledge the imprints of out of time ordered correlators on effective stochastic dynamics of Langevin systems. And they derived general constraints along the lines of the fluctuation dissipation theorem in coming from the out of time ordered correlators. So what we're after is really some kind of, if you want in quantum mechanics, let's say, what we're trying to do at this level is a 1pi action of the probe with couplings that are captured by the environment dynamics or environment correlators. So if I imagine I have my system action, which is no longer oscillators because it has non-Gaussianities, and my probe action, and some linear coupling between my probe and some effective operator of the system, insofar as the system dynamics is concerned, my environment dynamics is concerned, this Q is just a classical source at linear order. So if I'm trying to understand what is happening at linear order in these sources, I just need to know what the correlations of what the correlators of OX are in my environment theory. So just think of any effective field theory you write down. So if you want to do matching with UV physics, you just compute low energy data, and then you match with microscopic data. In this case, I'm claiming that the effective terms in the influence functional for my probe are simply dictated by suitable correlation functions of the microscopic system. And that's why the quantum mechanical problem is, in some sense, easy. Now, I'm going to motivate for you in a bit why this is worth studying in holography. And to do that, let me posit two statements, which I will explain as we go along. At this point, it sounds like if I'm doing Gaussian dynamics of quantum fields, or if in quantum mechanics, or if I have perturbative non-Gaussianities, you say, what's the big deal? Why can't I just keep doing perturbation theory? As we'll see when we go to quantum field theories, there are two issues. One is that you'd want the environment to be suitably thermalizing or suitably scrambling in order for you to be able to especially if you have multiple timescales, you have a hierarchy of timescales in the environment, you'd want to be able to decouple them so that you can write down an effective field theory which is local for the probe. That may not always be true, and one of the examples I will discuss later is the physics of hydrodynamics, of fluid dynamics, where there is the thermalization timescales in weakly coupled systems are actually quite large. So you have to integrate, you have to wait for a long time for the environment to suitably thermalize for you to be able to discuss what the low energy dynamics of the probe system is. So that's a problem. So that we can deal with by thinking about environments which are fast scrambling. And one class of environments that we all know and like, which are fast scrambling, are holographic environments. Black holes, as has been well motivated in various contexts, they have one great feature about them is that they have a set of fast scrambling modes where the dynamics, thermal dynamics, is completely dictated by temperature. Okay, so we'll try to use that to sort of try to at least structurally understand the effective field theory of such influence functionals. Okay, now not all environments will be such fast scrambling, but the claim I want to make is that the structural aspects of these effective field theories can be reduced by looking at the holographic system. And once we've done that, we can then use that to go back and study simpler systems like kinetic theory for fluids or gases, what have you. Okay, so which is why I'm going to pose the question, how do we take these statements and upgrade to QFT by saying, let me take insights from probes of holographic environments. Okay, so that's my sort of two-line pitch for why we should study this problem in holography, simply because holography provides us with environments or field theories which are strongly correlated enough with dynamics that is fast scrambling. Just to anchor yourself, let me give you a problem that just relates back to this Calder-Leggett model. And that problem is the following. It's just basically the same Brownian motion problem, but now seen in a slightly different perspective, from the perspective of holography. So imagine now you have a thermal plasma. I've taken n equals 4 super Yang-Mills plasma. That's my plasma from which has of a field theory that has a holographic dual. The details of this theory don't matter. But let's say you pick your favorite thermal plasma, and then you put a probe object in it. So in this case, I'm going to take thermal n equals 4 super Yang-Mills plasma, and I'm going to put a probe quark in this plasma. And the question I want to ask is, what is the dynamics of this probe quark? I expect that the dynamics is very similar to what I just saw in the Caldera-Leggett model, except that n equals 4 super-Yang-Mills plasma is not, at strong coupling, is not a collection of harmonic oscillators. So this is a non-Gaussian ensemble. So we should be able to deduce from here then its necessary non-Gaussianities and work out what the corrections to the stochastic Brownian effective field theory are. So there's a qualitative picture here, and since I'm not going to sort of dwell on this example in great detail, let me just spell out the qualitative picture and tell you where to find further details. The qualitative picture is the following. In a holographic plasma, a probe quark has a flux tube attached to it. The flux tube is a world sheet. It has a classical avatar at strong coupling. It's basically a classical string. If you just put a quark in this plasma, and the thermal plasma is dual to a black hole in ADS-CFT. So if you put a quark in a plasma, I'm putting a quark on the boundary of ADS. The string, the flux tube, dangles straight down from the boundary if the quark is at rest and enters the horizon. If you instead try to drag the quark, with some finite velocity, then this flux tube or string trails behind because of the friction. Okay, so that's the sort of famous trailing string solution found by Gubser in 2006. But you can use this model to ask one more question. So that explains the physics of friction. The flux tube gets dragged by the black hole thermal environment and loses energy into the black hole. That classical physics of stuff falling behind horizons is classical dissipation in this problem. So you might ask, where is quantum fluctuations? Where are the fluctuations associated with this dissipation? How does fluctuation dissipation theorem realize itself? And the qualitative picture is as follows. So if you think about what's happening to the string world sheet, the string world sheet itself has an induced geometry, which is that of a black hole. In fact, that of a two-dimensional black hole, because the string world sheet dangles straight through the horizon in the Lorentzian picture. And the thermal fluctuations on this world sheet horizon, i.e. Hawking quanta, which are amplified by lambda effects, so they're not 1 over n suppressed in this problem, they propagate up the world sheet and they buffet the quark, which then jiggles around and therefore shows the Brownian dynamics. Okay, so you see that in here the match is basically between the classical dynamics of the string world sheet and the quantum dynamics of Hawking physics. And this was something that was, as Albion points out, was first pointed out a long time ago by him and Emil, but then in the ADS-CFT context, some of us looked at this well 15 years ago. But there's a nice recent progress of systematic derivation in real-time holography in the first paper that was written on the subject by Logan Ayagam and various his collaborators. And I also want to highlight some work that I was doing a while ago, which will hopefully appear sometime, with a student at Brandeis, a former undergraduate here, Guillermo Grimaldi. Okay, so that's the story in the context of quantum mechanics. But let me pause here to see if there are questions, because now I'm going to jump up in complexity and go straight to field theory. Great. So now I want to focus on similar problems with linear probe environment couplings, but in a holographic field theory. So my environment is going to be a holographic quantum field theory on Minkowski space, and I'm going to have some. If you want to keep a proxy, keep as a proxy the n equals 4 super Yang-Mills, but I'm going to be agnostic. My environment is just an ADS black hole. I'm going to have some intrinsic probe dynamics and then a linear coupling between the probe and some operator of my quantum field theory, which I'll take to be a single trace gauge invariant operator. Okay, and this for ADS-CFT aficionados, let me say that this is a a nice implementation of a picture that was called the semi-holographic model of condensed matter physics by Faulkner and Polchinski, where you basically use holography as providing you inputs for modeling strongly correlated systems. Okay. So from what I've said, the data I need is basically to compute the effective field theory of my probe system. Is I need real-time thermal correlators from the holographic environment, and I therefore need to implement some kind of real-time boundary conditions for semi-classical gravity. This problem itself has a long history, and I don't know why Son got erased into something else. But so this problem was first studied by Son and Starinets in almost 2 decades ago. And then there are various pieces, several pieces of works that have tried to understand this setup. But I'll point out a new picture that was proposed a couple of years ago by Hong Liu and his students, which basically, I think, gives us a much better handle into this problem than anything else that came before. So let me, I'm assuming that most people here aren't fully familiar with Schwinger-Keldysh, so let me start by explaining some basic aspects of thermal field theory in real time. So I want to compute trace in my environment theory. I want to compute correlation functions of operators inserted at various times. And I want to compute them with a suitable out of time ordering. So I don't want, so if I take an endpoint function of n operators, there are n factorial time orderings, but I don't want to compute all of them. I want to think of this, the class of correlation functions that are basically a generalization of the following. I come into my thermal medium, I disturb it, and then I watch response. So I'm looking for generalizations of response functions. For 2-point correlators, the response functions are just retarded Green's functions, which is just the expectation value of commutator with a suitable theta function at finite temperature. But there are generalizations of this to higher point functions, so higher point retarded response. And then a nice framework to think about them is that we think about preparing the density operator rho beta is e to the minus beta h. So you imagine preparing this by a path integral in imaginary time by on a circle of period beta, and to insert Heisenberg operators, you just cut open this path integral, the Euclidean path integral, and do a real-time evolution separately for the Ketz and the Brass. So that gives you wave functions for Ketz and Brass. And then finally, you want to take the trace, and the trace is basically projection against the maximally entangled state. So you just project in the future on the maximally entangled state. And that defines for me the Schwinger-Keldysh contour. Where the separation between the Ket and Bra evolution is order epsilon. And so the time evolution in Euclidean time is beta minus epsilon.
This meeting is being recorded.
And I have these, and I have the evolution directions as indicated. And the set of correlators you can compute are correlators where you insert operators, and real time runs out this way. Okay, so this is t equals 0, let's say, and this is t equals some capital T, the latest time of interest. So you can just, and so you can't compute all endpoint functions, but you can compute all the retarded response functions in this framework. So the question is the following. So this is a well-defined thing in quantum field theory. And I'd like to ask, what do I do if I want to compute this in gravity? And one answer is the following. Well, let's go back to the 0th order picture. So if you wanted to compute the correlation function in Euclidean time, where you have the boundary being of ADS being a circle, then we know that at high temperatures, in fact, since I'm in Minkowski space, only the high temperature phase is dominated by a solution, which is one where the circle shrinks to 0 size in the interior smoothly. And this is the cigar or Euclidean Schwarzschild area, Euclidean black hole geometry. Okay, so that would compute for me, working in the Euclidean black hole in ADS spacetime would compute for me the Euclidean correlators with of the dual field theory. But I want to do something more. I want to take this boundary contour and cut open to allow myself to do real-time evolution. So I want to slice open a sliver of the cigar, and I have my, that's just this piece and this piece extended now in the radial direction of ADS. So this picture doesn't have real time yet, but you can put the real time back by evolving forward and back, and the picture you get is something like this. So this is my same picture. Now the cigar has been tilted some other way. So I have my cigar, I've cut open a sliver. In the boundary, I'm allowing myself to evolve one end of the sliver up in Lorentzian time and then bring it back. The future is this maximally entangled state. And I need to find a bulk geometry that sort of smoothly merges the cigar and is anchored on this boundary contour. That's the 0th order rule of ADS CFT. So we know what the Lorentzian continuation of the Euclidean cigar is. It's if you continue the Euclidean black hole, you get the Lorentzian black hole geometry. And had you cut the cigar halfway through, so had you exposed not the sliver that I did, but had you exposed the cigar by cutting open in the Lorentzian geometry, had you gone from this point on the boundary to the antipodal point on the boundary, you would be going in the Lorentzian Penrose diagram from this point on the boundary around off the plane, therefore you don't see my marker, onto the other boundary. But you can also go through this from this boundary to the other boundary by going through the radial direction. That's going like along the top of the cigar, through the tip, and back down to the bottom. Okay, so that's the geometry. But you see, we've now cut open the cigar in a very different way from the eternal black hole picture, and we've glued in these Lorentzian sheets. This gluing in basically means the following. It means that in order to compute retarded response, we should look at we should first of all realize that we have a ket piece and a bra piece and a ket piece in this geometry. So I have, if you want, one way to say this is I have two copies of the black hole, of the Lorentzian section of the black hole, one of which, the ket piece, is glued back here. The other is the bra piece is glued back on this cut of the Euclidean solution. How are they glued? How are they attached in the bulk? Okay, there we have some freedom. We have some freedom because all we are told is you have a boundary time contour that say starts out in the boundary at t equals 0 and ends up, let's say, at some future time t. So all we need is our bulk contour to end up here. So we could sort of deform this contour. It has to come back to the tip of the cigar, but it can do all sorts of crazy things as it comes back to the tip, as long as it does the same kind of crazy things on both the bra and the ket piece, because those will cancel out by bulk evolution. Okay, so in a path integral, a forward-backward evolution with no insertions is tantamount to a resolution of the identity, so you can just erase it. So I don't know how to implement such funny cuts, but one thing we do know, and this is the proposal of these folks, is you can, in fact, implement something nicer. You can basically study correlation functions for arbitrary late times by allowing the boundary time contour to run all the way to future infinity. Okay, this is not necessary for computing retarded response, but let's just focus on this example for simplicity. Then in the Lorentzian section, I end up keeping the full part of the domain of outer dependence, future of my initial time slice. So the piece I'm keeping is the shaded region of these geometries. In the ket part of the Penrose diagram, I keep this wedge up to the horizon. In the bra part, I keep something similar, except that time runs differently in the kets and the bras. So I'm going to work in coordinates where my time on the boundary maps to infalling time in the bulk. So time, sort of basically bulk time, falls in from observer who falls in this picture in my Lorentzian section, falls in through the future horizon, and then comes out now, doesn't fall into the singularity, but comes out, he or she smoothly goes around and comes out from onto the ket, from the ket to the bra part of the geometry. Okay, so in other words, if you want to think about the Lorentzian section, you keep two halves of the domain of outer communication of the black hole, which are smoothly glued across the future horizon. Okay, it's a very different geometry, and other analytic continuations that have been discussed in the literature. And this is not, for example, just to be clear to people who know the context, this is not the double cone geometry, which is also a different analytic continuation of the Euclidean black hole. Okay, so that's the space-time we're going to work with, but this is nice in terms of pictures. I'm going to give you some equations in a minute, how to do computations with them. But before I do that, let me pause again to see if there are questions. Okay. So what I argued for you is that Schwinger-Keldysh in the bulk should be treated as a two-sheeted Lorentzian spacetime, but I have a horizon, and the horizon, if you want, implements thermal boundary conditions. And the claim of these folks is that what you should do is you should implement a specific branch cut structure which encodes the physics of the thermal state. Okay, so a much simpler way to say all these pictorial things that I just said is the following. Imagine working with a complexified spacetime with two boundaries. The radial coordinate of the bulk is made complex and runs along a contour that encircles the bifurcation surface of the horizon with a branch cut that starts out of the horizon and runs towards the boundary. I'll choose the monodromies such that on one leg of the contour, there is the real part of this coordinate is 0, but as I go around, I pick up a unit monodromy. I've just normalized so that monodromies are real as I go around. Okay. In coordinates, in fact, one can just write down a nice metric. So in coordinates, this is, if I write down the following metric, which most of you would recognize as the infalling as a metric of a Schwarzschild black hole in Eddington-Finkelstein ingoing coordinates, I take the ingoing, I take the radial coordinate and replace it with a complexified tortoise coordinate, which for good reasons, we decided to call the mock tortoise coordinate. And it's defined with a particular normalization to implement this unit monatomy condition. Okay, so I've divided by a factor of 2 over beta to make sure that I don't get a factor of 2 pi going around, but I get a factor of 1. Okay, so that's the geometry, and the claim is the following: any calculation you want to do in thermal field theory of a strongly correlated system can be done by doing standard GKPW, Kapser, Klebanov, Polyak, or Wheaton type calculations in the usual ADS-CFT sense on this spacetime. Okay. I emphasize this has some very nice features. There are no ambiguities in this proposal arising from what do you integrate over. Do you have to worry about the fact that black holes have singularities? The thermal state of the black hole does not know about the singularities. It doesn't need to know about the singularities. You don't have to integrate over the interior region of the black hole. You can, if you choose to, by doing what I said of picking contours that do weird things and try to isolate those contributions, but it's not necessary insofar as obtaining thermal correlators is concerned. Okay. So let me spell out these rules and explain some more details. So for starters, let's imagine a very simple problem, the kind of problem that you would encounter if you're learning ADS-CFT these days. Maybe not anymore because no one computes correlation functions, but at least in the old days, we started by learning how to compute what the GKPW dictionary was and computing correlation functions. So imagine that the operator you're using to probe the system is a scalar primary of some dimension delta in the holographic CFT. Okay, so that you can write the dynamics for the dual field in some nice form, and these details don't matter for the purpose of this discussion. I'm just emphasizing that because I've changed coordinates to infalling coordinates, the Schwarzschild time reversal symmetry T to minus T is broken, but there's a relic of it in the fact that the infalling coordinates get swapped with outgoing coordinates under time reversal. Okay, this will be important in a second because it'll enable me to solve one problem that is easy to solve and get the full answer by doing some tricks. Okay, so just remember that I can implement time reversal by suitably mixing B and the mock tortoise coordinate, and you can write things covariantly if you like by introducing suitable derivatives in this suitable basis for tangent and cotangent spaces that are adapted to this time reversal isometry. So we have a simple wave equation, and you'd recognize that if I just wrote this as d by dr, it's the usual wave equation in the ADS background. And the claim is the following: to compute correlation functions which enter, again, as I emphasize, the effective field theory of our probe for linear couplings, compute first the ingoing Green's bulk to boundary Green's function with boundary conditions where you have some source for the field dual to this operator on the boundary, and you have regularity at the horizon. Okay, so I've switched to some kind of Fourier domain, and I'm computing this infalling Green's function in Fourier basis. Once you do that, so that's like saying on this picture, I'm working in just this sheet on the ket piece. I'm fixing sources on this boundary, and I'm allowing my fields to fall in, but I'm requiring that they're regular on the surface, which is nothing but the fold in this picture. So nothing, there's no singularity there. There's no strange thing happening. So the fields solutions in the bulk should be completely regular out there. Once you do that, and an advantage of writing things in this nice basis is the following: I can then figure out what is the corresponding bra solution that looks like the outgoing flux by using some tricks associated with the time reversal. So long answer short, you don't have to solve the problem twice. You solve the problem once for the infalling Green's function. And the outgoing Green's function is obtained by conjugating, by basically time reversing, frequency reversing the infalling Green's function and multiplying it by a suitable factor. Okay, this factor takes care of this conjugation fact, but importantly, it's the bulk analog of a Bose-Einstein factor. Realize that zeta has a real part which is either 0 or 1. So going between the bras and the kets, you get a factor of e to the minus beta omega. So in some sense, this is encoding the correct way of doing Hawking's calculation in real time, rather than analytically getting it from the Hartle-Hawking wave function in Euclidean time. Once you put these facts together, we can now do the following. We can have sources on both of the Schwinger-Keldysh boundaries and compute the bulk solution by writing down a full Green's function that refers to both boundaries. So I'll have sources. So if I redraw my picture, I'll have sources on the left and right. So I have some J lefts here and J rights here for the field phi. And again, I'm going to take linear combination so that J average is J left plus J right over 2. And J difference is J right minus J left. I can then write the bulk solution on this geometry, which we decided to call the GRSK solution because it's a gravitational Schwinger-Keldysh solution, in terms of the infalling propagator multiplying the average source, and a new propagator, which by right should be called the Hawking propagator because it has both the outgoing mode and a suitable Bose-Einstein dressed infalling mode, okay, times the difference propagator. And now you see that the source, there's one piece of data I wanted to keep in mind. The sources coupled to operators in my average difference basis as follows, because the switch between the average difference basis is like a light cone switch. So if I have J right O right minus J left O left for kets and bras, that switches to AD type couplings between sources and operators. So I have a Green's function written out in this nice way, and I have sources for the left and right fields, or for the classical and quantum fields. So I can just compute arbitrary correlation functions. Bonus, you actually don't have to do anything fancy because I already told you that the outgoing Green's function, and therefore the entire Hawking Green's function, is completely dictated by the infalling Green's function. And second, if you think about doing these calculations as contour integrals, then the Schwinger-Keldysh correlator picks out a discontinuity across a contour. So you can just evaluate, once you've gone through all this discussion and set up the problem correctly, you can just as well work on the ket piece, but the integrand in the GKPW dictionary is more complicated than before because it knows about the monodromy you pick up as you go around the cut. Okay, so that's the essential dictionary. And once you do this, you can just compute. Okay, and so there are various results that I can just show you, but just to emphasize that you can actually do non-trivial things, you can compute these in examples where the wave equation can be solved pretty explicitly. So in 2 dimensions or ADS3, everybody knows that the BTZ solution is just a quotient of ADS, so we know all the Green's functions. So in that case, you can just compute the classical quantum and the quantum fluctuations for a thermal operator of dimension delta. And you can compute higher point functions, and we gave some results for 3-point functions. I didn't write them down because they're not pleasant, but they can be obtained similarly. They're given in terms of some kind of hypergeometric functions or Maya G functions. And you can get similar results, but in higher dimensions, you're constrained by the fact that the wave equations and therefore Green's functions are not analytically obtainable in closed form. But you can make progress by asking the question as we asked, what is the effective field theory, which basically means you can do gradient expansions at low frequencies and low momentum. Okay. And what you end up with, if you translate the correlators of these operators into a stochastic theory for the probe, you can write down the analog of Langevin dynamics for probes in quantum field theories. So what you find is a structure very similar to the Langevin structure. I'm missing some term here, missing a psi A here. And so you get the difference, the quantum field of the probe coupled to some derivative of the frictional derivative operator acting on the classical field. That's like the classical Langevin dynamics. And now, since I have broken Lorentz symmetry, the kinetic terms along the time and the space directions don't have to agree. But I also get a series of fluctuation terms, which you can be computed to order one desires. We only focused on contact interactions in the bulk, but it's not hard and it should be possible to do non-contact terms. Okay. Payoff, you of course recover fluctuation dissipation type relations as you expect, but you also get the nonlinear analog of them coming from higher point functions. So these are non-Gaussian fluctuation dissipation relations, which if you like, encode the non-Gaussianities of the thermal plasma of n equals 4 super-Young means as seen by this probe. Okay, so a probe that actually couples to a scalar of dimension delta. So this is nice. So first of all, we verify from holography that the paradigm that we would like to say just works. There are some features that I'm not going to discuss here, which has to do with the fact that the sources actually get renormalized. Those renormalizations are interesting to understand, and they have had. But let me elide over the technicality for a second because I want to say something else. But this program can be carried through to whatever order. So we have a structural way, and I would say a principled way of deriving such effective field theories for probes associated with regular fields in the problem. But unfortunately, this can't be the full story. And the problem is the following. I motivated the story by saying, look, in quantum field theories, if you have plasmas, there are some operators that are fast scrambling, but there are some operators that aren't. So the class of operators that I just discussed to illustrate the point are fast scrambling operators, which thermalize, if you will, if you disturb them, the plasma thermalizes, rethermalizes, it re-equilibrates in a time scale roughly of order the temperature. How do I know this? I know this because I can go and look at the corresponding bulk dynamics and ask, what are the decay time scales associated with the bulk field? But the decay time scales, as I said in the example of the string, are associated with stuff falling behind horizons. Stuff falling behind horizons in classical language is basically just quasi-normal mode dynamics. So I can just ask, what kind of quasi-normal modes do operators of this kind have? Well, if it's an operator of dimension delta, the delta details don't particularly matter, but the quasi-normal modes, all I need for now is that they're gapped from zero frequency by an amount roughly of order temperature, thermal scale. This is true for almost all operators, but not true in particular for conserved currents. So the conserved currents in the problem have very different dynamics. And in fact, they actually have long-lived quasi-normal modes. And this is the origin of hydrodynamics, as Polycastro-Son and Thorinets pointed out in ADS-CFT. So they include things like momentum diffusion. It says that, you know, if you try to shear a fluid, you get diffusion, but it propagates very, you sort of, momentum wants to sort of re-equilibrate the shear, but it does so by very slowly diffusing it through the medium, and it has very long time imprint. Or you could try to propagate physical energy through the system and through a plasma, and you excite phonons, but phonons propagate, but they also attenuate, but the attenuation is very slow because the attenuation also is diffusive dynamics. So now if you try to compute the effective field theory for probes that couple to such operators, having integrated out the environment, there is no local effective field. Why? Because you're integrating out goldstone modes or moduli associated with these soft modes. So zeroth order statement, and this is something that people have pointed out before, is that once you include fluctuations, there is no 1PI effective field theory for examples of retaining moduli. So what one should do is do what we know how to do in regular quantum field theories, is to implement a sensible Wilsonian effective field theory by not integrating out such moduli, but rather writing down the effective field theory in terms of them. So this is easier said than done for the following reason, which I'm going to explain in a very simple example. So imagine just a conserved current, okay? Just single conserved current in the field theory. Let's say it's a U1R inside SU4 in n equals 4 super Yang-Mills. That conserved current couples to some bulk Maxwell field. The coupling is basically operator coupling to source. Now I can split this Maxwell field into various pieces. I look at a direction of propagation, and I look at how the modes, how the photons are organized under a little under representation into governed by the rotation group in the plane perpendicular to direction of propagation. So the SOD minus 2 little group. So there are d-1 physical photon degrees of freedom. d-2 of them are physical, they're short-lived, they just vamp by falling behind the horizon. One of them, which is some combination of these three naive vector degrees of freedom, is long-lived and corresponds to charge diffusion. So claim, and this is, I think I'm getting close to my end of time. I'm gonna have like 5 minutes. Don't have a host, okay. So I claim the following. So you can understand various of these. So you want to first of all figure out how to encode the physics of these guys. And second, what kind of effective field theory should you write down by separate? Well, you can see two problems. One is that the current itself has both long-lived and short-lived modes. So if I talk about coupling to the current en masse, I have no easy way a priori of distinguishing these long-lived and short-lived modes. So I need to do something further. I just showed you a trick which involves suitable representation theory decomposition, which isolates, at least at the quadratic level, the long-lived and the short-lived modes. Okay, so let's take this idea and proceed further. So the claim is that you take this decomposition seriously and repackage the dynamics of your conserved current in the bulk in terms of variables that directly talk to the long-lived and short-lived modes. And then magic happens. And this magic, I think, really has to do with the fact that holography is fantastic. Okay, so claim is that you can repackage all such dynamics in terms of a class of probe fields with a non-trivial background coupling. Okay, so I have written an equation here, which if you want to compare with, I have introduced a parameter M, and this parameter M is like my proxy for a massive field. I've switched off the mass term here, and d-1 has become M. Okay, but M is important because M is what we refer to as a Markov unity index, because it tells me what the nature of my probe is doing, whether it's coupled to a long-lived or a short-lived mode. And I'm going to give you a cartoon picture in the last few minutes of what we have, and I'll just end with I can explain in detail how we know this in various examples. So the claim is that holography provides a paradigm where you can study even these long-lived modes. And the paradigm is as simple as this. You study the physics for understanding the Gaussian problem of a probe scalar field non-minimally coupled to the gravitational background on this Schwinger-Keldysh geometry. What is the nature of the non-minimal coupling? The non-minimal coupling is provided by an effective dilaton, a background dilaton, which basically modifies the measure root G in the scalar action. And what you get is the following two classes of answers. If you have probes that have short-lived quasi-normal modes that decay away very fast, physically what it means is that such probes have wave functions that fall into the horizon very quickly and don't hover around near the bound. It translates in this non-minimal coupling to saying that this dilaton factor, which provides the non-minimal coupling, is growing rapidly near the boundary with a power that is in this parameter. I have parameterized this power so that I can remove this root G. So I can just talk about R to the M as asymptotic behavior. As long as M is bigger than a certain amount, then this behavior is Markovian. Okay, I'll qualify what this boundary condition means in a second. On the other hand, long-lived modes behave exactly the opposite. They're absolutely floppy near the boundary. They have no potential barrier to entering, being hovering around the boundary. In fact, they have some reluctance to fall into the horizon. So their potential is actually doing exactly the opposite. So this dilaton coupling is weak near the boundary, is switching off. In fact, so the field just hovers there, but it sort of penalizes the field from falling in. And the paradigm can't be any simpler than this. There's just one parameter, this M, the index, which says whether your field is Markovian or non-Markovian. And you can see how this works, and I'll explain after the talk how we know this to be true and what examples we know this to be true. And the claim is the following: if you are trying to compute correlation functions of these currents, as long as this Markovianity index is greater than -1, you compute them with Dirichlet boundary conditions. That's the usual GKPW dictionary. If you have these non-Markovian modes, the ones which have long-lived quasi-normal modes, their correlation functions are computed with Neumann boundary conditions. And if you want to not integrate them out, not compute the generating function of correlation functions, you should Legendre transform the correlation functions from a 1pi effective action to Wilsonian effective action, which means you should quantize these fields also with Dirichlet boundary conditions. So with that said, I'm just going to flash by saying there is an effective object, which I'm going to say is a Wilsonian influence functional, parameterized by sources for these long-lived, for the short-lived modes, and waves or fields for the long-lived modes, which has a nice following structure for the Wilsonian effective action. Again, I've written everything in terms of these average difference fields, and the only piece of data, the quadratic order, are Green's functions and inverse Green's functions, which we can compute. You can do nonlinear, you can do non-Gaussian stuff, which we can write down simple time models and compute with them. But you can also do non-Gaussian stuff in physical problems because they're easy to compute. They're harder to compute in terms of vertices, but once, just as everybody has computed correlation function, the usual vacuum in ADS-CFT, they can be done in these examples. So I think I'm not going to flash for you the results that we have, but I'm going to just say that holography provides a useful paradigm for studying open effective field theories. And it actually gives us, I think, a very nice way of packaging the information about what is short-lived and what is long-lived in terms of effective fields propagating in a fixed background. Of course, one would like to do more. One would like to allow them to back react and so on and so forth. But at the outset, at least, the linear problem of open quantum systems, I think, has a very clean solution in the context of holography. Let me stop there.
Thanks, Mukund. That was great. Okay, I'll stop recording now, and people should feel free to ask lots of questions.